All right, we're now at section 18.4, Kirchhoffs rules and complex DC circuits. Let's find the PowerPoint, and here we are. All right, as you have seen, we can analyze simple circuits using Ohm's law and the rules for series and parallel combinations of resistors. There are many ways resistors can be connected so that the circuits formed can't be reduced to a single equivalent resistor. To analyze more complex circuits, we will make use of two simple rules called Kirchhoffs rules. Number one, the sum of the currents entering any junction must equal the sum of the currents leaving that junction. This rule is often referred to as the junction rule. Number two, the sum of the potential differences across all the elements around any closed circuit loop must be zero. This rule is usually called the loop rule. The junction rule is a statement of conservation of charge. Whatever current enters a given point in the circuit must leave that point because charge can't build up or disappear at a point. If we apply this rule to the junction in the figure on the left, we get the current equation shown. Oh, I think it was already showing. The figure on the right represents a mechanical analog of the circuit. In this analog, water flows through a branched pipe with no leaks. The water flow rate into the pipe equals the total flow rate out of the two branches. The loop rule is equivalent to the principle of conservation of energy. Any charge that moves around at any closed loop in a circuit, starting and ending at the same point, must gain as much energy as it loses. It gains energy as it is pumped through a source of EMF. Its energy may decrease in the form of a potential drop minus IR across a resistor or as a result of flowing backward through the source of EMF from the positive to the negative terminal inside the battery. In this case, the electrical energy is converted to chemical energy as the battery is charged. Okay. When applying Kirchhoffs rules, you must make two decisions at the beginning of the problem. Assign symbols and directions to the currents in all branches of the circuit. Don't worry about guessing the direction of a current incorrectly. The resulting answer will be negative, but its magnitude will be correct. Because the equations are linear, I lost my place, I'm sorry. Because the equations are linear in the currents, all currents are to the first power. When applying the loop rule, you must choose a direction for traversing the loop and be consistent in going either clockwise or counterclockwise. As you traverse the loop, record voltage drops and rises according to the rules shown in the figures. As you can see in the top left figure, if a resistor is traversed in the direction of the current, the change in electric potential across the resistor is minus IR. If a resistor is traversed in the direction opposite the current, as in the top right figure, the change in electrical potential across the resistor is plus IR. If a source of EMF is traversed in the direction of the EMF, from minus to plus on the terminals, the direction in electric potential is plus epsilon. If a source of EMF is traversed in the direction opposite the EMF, from plus to minus on the terminals, the change in electric potential is minus 2 epsilon. To solve a particular circuit problem, you need as many independent equations as you have unknowns, and you end up solving simultaneous equations. Now, let's look at some rules, some strategy rules for applying Kirchhoffs rules. Number one, assign labels and symbols to all the known and unknown quantities. Number two, assign directions to the currents in each part of the circuit. Although the assignment of current directions is arbitrary, you must stick with your original choices throughout the problem as you apply Kirchhoffs rules. Apply the junction rule to any junction in the circuit. The rule may be applied as many times as a new current, one not using a previously found equation, appears in the resulting equation. apply Kirchhoffs loop rule to as many loops in the circuit as are needed to solve for the unknowns. To apply this rule, you must correctly identify the change in electric potential as you cross each element in traversing the closed loop. Watch out for signs. Number 5, solve the equation simultaneously for the unknown quantities using substitution or any other method familiar with you. Just solving simultaneous equations. Number 6, check your answers by substituting them into the original equations. Okay, this ends this section. The next section will be section 18.5 RC circuits, which is sort of a review for you since you've done the RC time constant experiment.